Right. Good afternoon, everybody. Hi, my name is Saul Matthews. I'm the commercial director at Synaptec, and welcome everybody to another one in our series of regular webinars where we're focusing this time on cable fault detection. Now, as normally happens in these webinars, everyone's running back to back in online meetings these days. So we like to give everyone a few minutes to log in, and I can see the numbers are zooming up while I'm talking. So let's give everyone a few minutes to settle in and join in. A few housekeeping notes for everybody to be aware of. First of all, you'll find as attendees that you are muted during this session, but we do invite you to use the Q&A button below on your screens in Zoom, not the chat button. That's not enabled for this session, but Q&A. If you've got questions that we provoke that you feel we're not answering either thoroughly enough, or you've got more specific questions that maybe are specific to your business or particular issues and operational challenges you have, that's fine. Put them in there. We'll try and answer those live in writing as we go along. If we can't get to it towards the later part of the webinar, I'll try and summarize the most important and frequently occurring ones and ask the panelists to speak to them. And of course, if there's anything too detailed that will take too much time, we can always respond to you one-to-one after the event. Now, that said, again, the conversation point today is cable fault detection. And what we're going to be doing is taking you through a few slides about us and about the technology and what we're doing here. And then I'm going to introduce our team. That should take about half an hour, and we want to make sure there's plenty of opportunity for questions and answers. We're going to be putting some polls up as we go along as well. And then at the end of the event, of course, we will have recorded it. People who have attended or registered to attend will supply you with copies of an edited version of that you can access through YouTube, private links, and also, of course, on our website at Synaptec, that's synapt.ec. You'll find white papers, case studies, and documentation referring to products, component technologies, and application case notes. So with that said, I think, Neil, if you're driving, you want to click onto the next slide for us. I'll head into this now. I've stalled everyone for a few minutes, and we'll try and finish on time and be respectful of people's time. So today, we have got Dr. Philip Orr, who is the Managing Director and one of the co-founders of our technology, joining us to speak. We've got Stephen Blair, who is our lead power systems expert, and Neil in the middle of your screen, if you can see all of our videos feeds at the moment. Neil, he looks after our engineering team who are responsible for the sensor technologies and the hardware. And in a moment, we'll have Professor Campbell Booth joining us, who, of course, on one hand, is our applications director at Synaptec, but on the other hand, he wears another hat. Of course, he runs the electrical engineering department of Strathclyde University and is a world-recognized expert in protection systems, especially for HV grids. Good timing, Campbell. You just joined. Hello. All right, Neil.
Yeah, thanks very much, Saul. I heard you just introducing me there, and I'm sorry I've had some IT issues at my end, so apologies for being a wee bit late.
Don't worry, your audio is okay, and that's what counts. Neil, if you want to just punch things along to the first slide. So the agenda today is we're going to do a brief discussion about who we are. We're going to introduce the subject of overhead line monitoring, and then we're going to look at rephase, and that's our technology product, how it applies for CFD applications, and then open up the discussion from there. Now, I will be honest with everyone, this is the first time we've run a debate like this and tried to have more interactive sessions. That was a request from customers and partners around who said, you know, we want to be cautious of not just explaining our technology at you all, but trying to engage and also get some feedback as well. But I do have to do this part because some people don't know us, and I've noticed there are over 100 people trying to take part today, which is wonderful. But we do need to explain because we are new to some of you. So very quickly, Synaptec, if you boil it all down, we invented distributed sensors. That means arrays of completely passive mechanical and electrical sensors that can be deployed over wide areas, only connected back to one central point by optical fiber, which means you can have hundreds of sensors over very wide distances, synchronously and permanently streaming information about currents, voltages, but also temperatures, vibrations, and strains over very long distances, which means we can do longer range, lower cost per location, and do that at unprecedented speed with no sacrifice to quality or performance or accuracy. And you can see across the bottom here just some reference points in our recent past and actually ongoing right now, where we've already deployed these systems with customers like Scottish Power and SSE, who are transmission operators in the UK, Statnet, one of our key partners in the Nordic region. In Finland, you've got the Catapult, who have helped us demonstrate our technology for the first time offshore about a year and a half ago, where we were instrumenting cables and subsea cables for improved visibility and control. That's been scaled out now by Vattenfall, one of the big offshore wind developers. And most recently in 2021, we're deploying new sensor systems to help Red Electrica in Spain and also Deutsche Bahn in Germany, all related to medium to high voltage power system management. It's designed, of course, for the mission critical roles of protection and control in transmission systems, but because it achieves those levels of accuracy and dependability, it just so happens that our technology is very good for the automation of condition monitoring of remote or very inaccessible assets that are out there on HV and MV power systems. So keep that in mind when we move to the next slides. But that's the very quick overview of our company. And then moving on from that, I'm going to hand over just at this point here to ask and invite Campbell and the team to get into the subject matter at hand. But as we do, I just wanted to launch a very quick poll and take a quick snapshot of opinions here. So if all of you wouldn't mind for just 10 seconds or so, could you quickly give us a yes/no answer to this initial poll? We wanted to understand how much experience is out there of undergrounding sections and having to instrument them distinctly from overhead circuits. Kind of an obvious, gentle question this, because as you'd imagine, everyone's going to say yes. That's why you registered for the poll. But there's actually a significant percentage of people who haven't done it yet, so that's interesting. All right, I think that's most people that have voted already, so it's a good sort of...
Let's give it a couple more seconds, so it's still piling in.
Yeah, that's taking up 40 seconds. Oh, there you go. That's almost 85% of you have voted now. So we've got a, I'm going to say 60-40 split to say yes, most of you have got some experience or knowledge of undergrounding sections and overhead circuits. Okay.
Okay.
I'll hold that thought. Campbell, can I ask you to pick up from here?
Yeah.
And then when you're ready, we'll go and do the next ones in a moment.
Yeah, I think there's two more polls to be run while this slide is on, but you know, it's clear that there's a lot of interest in this. There's a lot of attendees here today, so there's clearly quite a bit of interest in undergrounding and what the ramifications of that might be. So one of the things that you can see here, it's rather out of date, but you know, in terms of a survey that Seagrey carried out, you know, back in 2007, we can see here that you know there's a significant, and I would say growing, proportion of AC circuits, which would typically be at the high voltage, you know, overhead, being moved either completely or partially underground. And I think it's the partial undergrounding that's really more of interest and potential focus here today. But you can see that there's an increasing trend. Ofgem, again going back a few years, there was a £500 million fund which the transmission system operators were using to underground circuits through areas of outstanding natural beauty. I'm also aware personally of a number of long circuits in the UK where there are several sections where the cable section is either underground or, you know, maybe in a bridge or a tunnel as it passes through certain areas. Some other statistics here, you know, 37% of new transmission circuit length in Scotland over the 10-year period was underground. And there's a significant proportion. Of course, internationally, this is also happening. I'm aware of Denmark had a big programme to underground massive sections of its overhead network. And what we're here today to understand is that is how much, you know, this is an issue and what the specific natures of the issues that this may raise. So Saul, I think maybe we can move on to the second poll.
Thank you, Campbell. Yes, we'd like to know from all of the attendees here, what actually are the key drivers for undergrounding? It's a multiple choice answer, so please fire away on the polls. We've got environmental consideration, avoiding areas of outstanding natural beauty, reliability issues, avoiding obstacles, obvious ones like roads and waters or mountains. And of course, there's a public safety one as well. So while those results flow in,
Yeah.
we'll give those another 10 seconds because plenty of people are still clicking.
And it certainly seems that all of the issues are fairly significant. Environmental consideration seems to be dominating slightly, which is kind of tied in with the areas of natural beauty. But it seems to me as if we've got the poll options pretty spot on there, because it looks as if they're all fairly significant, important drivers for undergrounding.
Yeah. Shall we just share those results with everybody? There we go. It's quite evenly spread.
Yeah.
Okay, I'll move those out of
So
the way.
I think we've established that there's certainly a trend towards it, and that there are also, there's multiple sort of individual issues driving that trend. I think we've got another poll that we can maybe just run just now, so.
Yep, so the last one we wanted to ask all of you about was this one. I'm just launching now. Forgive me if there's any delays. What would everyone in the audience think are the main operational challenges which are presented by instrumenting hybrid circuits? Again, we kept this multiple choice, so we know that there's a lot of requirements for having discrete auto reclose functionality, but perhaps there are other reasons as well. We can't give you a free text field for the other, but please do your best to give us some direction on this because it's of interest.
Yeah.
That's most. I will just stop the poll. Yeah, now we're over getting to 80% of everyone answering. Then I'll share those with you. There you go.
Okay, so again, it seems to me that the kind of predominant challenge is in fault finding, and I suppose that's kind of linked to protection, backup protection, and certainly to auto reclose, because one of the main things, of course, with a cable circuit is that if there's a fault on it, then it's highly likely that it's permanent, and you certainly don't want to auto reclose onto it because that could cause even more damage, and potentially there's safety aspects there. But all of these issues are interrelated, but it's clear it's trying to identify where that fault is, and that's a function that's important for protection, for the actual recovery or remedial work on that fault, and also clearly for the auto reclose, because if you know it's overhead, probably a transient fault, so you can reclose. If it's underground, then you don't want to do that. So that's very
interesting. Perhaps there's an interesting distinction that we can discuss later about the difference between faulted section identification and fault location, because I guess some people in the audience might be thinking fault finding means precisely where that fault is, whereas enabling auto reclose block functionality could be done simply by knowing the section the fault lies in.
Absolutely.
You may in some situations want both or just one.
Yeah. So I think this slide is really our kind of reflections on that. So it's clear that, as I said, there's this trend, there's many drivers, there's potential challenges. And we say that fault finding and repair is more complicated, clearly, as we've seen there. So I think this is maybe moving on, and I'll be handing over to Neil in a second. But if we can have some way of instrumenting the cable sections separately from the overhead, there's potential benefits. But you can see here that it's at the moment, it's prohibitively expensive and complex. There's a lot of reasons which make individually instrumenting and protecting or monitoring those individual underground sections somewhat difficult and challenging. So we need a simpler solution and something that's scalable. And you see here on the final point, we're talking about auto reclose blocking, but of course there are other potential applications if you have measurements at multiple locations on a circuit. And I should say, and I think maybe Philip will pick up on this later, you know, we're not just talking necessarily about measuring current and voltage here. We can measure temperature and other parameters which can be useful, maybe not so much from a protection perspective, but more for a monitoring and asset sort of management, integrity monitoring.
Yeah, I think that's a good point. We'll come back to that a bit later, touch on it. I think in the transmission and distribution sector, people are interested in auto reclose. Well, our impression is that that's the focus there. So it's about current differential, enabling that remotely at a low cost with reliability. Some other sectors, though, in power, but say offshore and renewables and so on, they're interested not only in faulted section, but also what is the reason for the fault and the precursors. And there's been quite a lot of research done on what are the common failure modes. Can we identify the common failure mode between the conductor itself and the terminations? And then in those situations, it helps to have a bit more contextual information around, just rather than simply detecting the fault and knowing whether you can, how to react, seeing the precursors in advance from mechanical signatures or even electrical transients. So we'll talk a little bit more about that advanced functionality later.
Okay, thanks, Philip. So I think at this point I'll be handing over to Neil to take us through the next few slides. Thanks very much.
Yep, thanks, Campbell. So I'm just going to talk about what Synaptec's approach is to solving some of these problems. So this will be using our rephase system to do cable fault detection and enable auto reclose at a distance and enable differential protection at a distance, as Philip says. So our approach to this is relatively simple, we think, requiring only 2 hardware components to be installed. So first of all, there's an interrogation system, our interrogator. This is the only powered and time synchronized device in the system. So that's typically installed in the substation. And that does the job of collating information from our sensors and communicating the auto reclose blocking signal or any optional SV streams to the SCADA or protection systems that are there already. And we can communicate via Goose or by dry contact for legacy systems as well. Just one of these interrogators will support up to 50 remote passive fiber optic sensors. So for this application, the sensor is our photonic current transducer, which you can see there on the right-hand side. This is essentially just a industry standard iron core current transformer, split core or solid core, depending on the installation. And the secondary side of that is instrumented by our passive fiber optic technology. So these are installed for this application at the transition platform between the overhead line and the underground circuit. And you don't require any additional hardware at that point, like multiplexers or any supporting infrastructure to install these sensors. Really, you just need to install a split core CT and do a single mode fiber splice into the existing fiber network. And then that fiber network backhauls that information back to the interrogator. So that can be done using the existing OPGW fiber or anything like that. We can install dozens of these sensors kind of daisy chained down a single fiber, and that can reach out to a nominal distance of about 100 kilometers from the interrogator location. So it's very long distance and scalable. Uniquely for this system, and possibly this is a bit of an extension beyond CFD, but because we can publish the sampled value streams at the interrogator from each sensor in the array, that allows us to publish continuous point on wave data from every single sensor down that fiber. So it gives you quite extensive visibility over a very long distance. So that's kind of the core of the system there. So there's particular kind of unique benefits of this system as regards CFD in particular. So as I've said, because these sensors are completely passive, it means they don't require power, time clocks, buildings, comms, or copper on the secondary side. You don't need any of that stuff at the sensor location, which means that every installation is very safe and quick and simple. You know, there's no non-standard processes involved in that installation. It's just, as I said, mounting of a standard industry standard CT and single mode fiber splicing. And because of the unique way we make our measurements in the fiber optic itself, they're immune to kind of disturbance of the fiber and immune to electromagnetic interference over distance. And all of this means that the system is very scalable as well. The sensors are connected in series or in parallel down the existing fiber network as required. It's a very large number of sensors that you can install over that long distance. And if there's only a few fibers available, normally there's many fibers available, dark fibers in the OPGW that we can use. But if not, then we can always share that fiber bandwidth with other technologies. So it's a very scalable and kind of quite unique system in that way.
In terms of the sensors, Neil, is it worth saying a few words perhaps for the audience about temperature effects, temperature compensation, given that these sensors could be deployed in quite a remote cable region where there's cable far away from anything that would permit active compensation to go on?
Yes, that's a good point. So again, inherent to the technology, as well as allowing us to get this kind of continuous point on wave at a distance, each sensor also passively communicates its local temperature. So that allows us to, in advance of installation, we would calibrate all these sensors in the lab, and then we are able to measure the temperature passively and then actively compensate for any changes in temperature in the environment, which means we can keep it to a nice linear performance over temperature. Really over this very wide temperature range, -40 to +80 as nominal, and then we can go to extended ranges if that's required for particularly extreme environments. Okay, so just moving on to kind of some examples of how this installs for the CFD in particular. So we can support the kind of the two different methods really of doing this, kind of simple and more advanced, which would be the earth overcurrent, where you might only require one measurement on the earth sheath in order to do a kind of simple CFD application, or the more in-depth kind of full differential protection, or CFD in that way. So either way, it's very simple to do because of the ease of installation of these sensors and the lack of any supporting infrastructure at that installation location. So really depending.
I wondered, Neil, sorry to interrupt you. I wondered if Campbell or Stephen might want to comment on the difference between those two, and in what situations you would want to rely on just the sheath earth current to detect that fault, and why in some situations you would want to have true differential current. Why is that preferable in some situations?
I think my take on that, Phil, would be it really just depends on the nature of the installation itself and the type of fault that you have. I mean, differential current will capture every type of fault, you know, phase to phase, phase to earth, phase to phase to earth and stuff like that. Clearly the earth overcurrent protection will only catch a fault if that actually involves earth itself. So you'll catch the vast majority with that. Some cables are three-phase and either the sheath or there's a separate earth core. Some it's three individual you know, phase cables itself. So, you know, differential will capture everything. Earth overcurrent will capture those that involve earth. So I think that's probably
trade-off between simplicity and cost on the one hand, and the reliability of it catching every single type of fault possible.
Yeah, absolutely.
I think that's a pretty comprehensive answer. The other thing is if you're monitoring the phase currents, then you get a few bonus features from that as well. Like we can look at the power quality in those phase currents as well, and also generate synchrophasors as well if that's required. So protection, as Campbell says, that's the main distinction is.
And I think, you know, the main thing for us as well is we're not really proposing this as a full-blown protection solution, although it can be, but what we're talking about here is faulted section identification. So, you know, either of those techniques will probably catch the vast majority of faults in the section.
Yeah. Thanks.
So just another couple of examples here showing kind of the scalability and the flexibility, I suppose, of this system. Because we have that long distance and because we can really route the fiber in any way that's appropriate with the existing system in order to connect sensors that are maybe multi-section along a single line, or if we had multiple feeders leaving a substation, say underground, those can be instrumented in parallel by the fiber. So it really depends on what the operator has in place and what their kind of philosophy is for protecting these sorts of schemes with one or more systems.
Neil, can I just interject at that point, because there was a question raised from the audience which I thought would be relevant just now since you're on this slide. So the questions that I've seen here are about are our sensors therefore only installed at termination points, or could they be used joint based to focus on more localized likely fault areas, such as so think joints and link boxes as an example?
Mm-hmm. Yeah, I mean, really, we can be installed anywhere where there's access to the electrical signal you want to measure, say that's the cable that you want to instrument, and second would be a convenient place to route the fiber. So
if
anywhere.
I might pick up on that, Neil, it's just I can see the question here, and I think the questioner is specifically wondering if we can distinguish between some different likely fault areas. For example, between the cable and the joint. And to do that with a differential scheme, yeah, you can be absolutely discriminative if you put the sensor before and after the joint, for example, and that's certainly possible. So the answer is yes. On the next slide, actually, we're going to talk about slightly more advanced functionality where you can do that and also look at some additional functionality. Do you want to pick up on this one, Neil, and we can see if any questions arise while we're going through this?
Sure, of course. So everything I've been talking about, or we've all been talking about so far, has been on the kind of terrestrial transmission and I guess what you would term classical CFD side of things. But what we've realized from working with some of our partners in the offshore world in particular is that you can gain a lot more information from adding more sensors to these locations, and you can get kind of more enhanced monitoring at these points. So for instance, at cable terminations, these are known to be a point of failure in the offshore sector in particular, and things like offshore wind farms and places like that. And we found there's a lot of value in not only instrumenting the primary conductor to get information on kind of current differential and things like that, but also the sheath current to look at, again, earth faults and things like that in that location, and then enhancing that with direct measurement of the temperature of the termination points. And all that allows you to build up a kind of holistic view of how that particular termination is operating, and then allows you to develop things like prognostics and look into precursors of faults. Yeah. So not only are you kind of responding quickly to faults and being able to diagnose them with all those extra measurements in there, but you can also think about predicting degradation of these points.
Yeah, I think from my perspective, the offshore sector has come at this in a slightly different way, because I think in the T&D sector, the cable fault detection is augmenting protection systems by allowing them to reclose. In the offshore sector, there's a slightly different business model, and they're interested in understanding why the faults are happening so that they can then mitigate them in advance or change the way they build the systems so that the faults don't happen in the first place. And in their situation, they know the joints are vulnerable points because they're points of physical connection. They can result in PD activity, they can result in transients, and they can result in resonances that give rise to voltage spikes, and these can lead to degradation over time. So not only do they want to catch the fault and be discriminative about which section is faulted, for example, between different generators, but they want to analyze the signal in depth, and they want to look at correlations between what's happening electrically with transients or or harmonics, and what's happening mechanically with vibration and temperature. And they also want to look at the correlations between what's happening on the earth conductor and in the phase conductors as well. So one thing that I'm quite interested in seeing if there's any feedback from the audience about this is, do we think that this is how T&D might go in future, having that level of information if it was available? Because one of the ways that we at Synaptec think of this is, if you have a Synaptec system in there, you've got 50 measurements to play with. If you deploy something if you deploy sensors out there to cost effectively do cable fault detection, you've got a budget of sensors that's unused. So what other information could be brought in to make that monitoring system more comprehensive? And how would we link that into giving the protection system what it needs to do auto reclose block, and giving wider SCADA and condition monitoring systems what they need to be more analytical about the reasons for those faults and spotting them in advance in future? I guess personally, I feel like that's a good way for T&D to go. But there has to then be some collaboration between the protection engineers and the asset managers, probably. I don't know if you've got anything to add to that, Campbell or Stephen.
No, nothing from me, Philip. I think that's a fair enough comment.
I would just say that I think it's fair to say that the cables themselves are perhaps under instrumented at the moment. And I think there's a lot of interesting things we could learn from both electrical monitoring and from mechanical and thermal monitoring as well, and to really help identify the cause of failures that are being experienced.
Yeah, I guess what I'm saying and what you're saying is that the fault is the end result, but there's a lot that goes on before that that could potentially be seen, so that you could act in advance and not experience an outage if you could make corrections, or schedule outages to make corrections rather than have an unplanned one.
Yeah, I mean, I think there might be differences. Clearly, obviously, here we're kind of talking more about offshore and subsea, but I know there's certainly been quite a few incidents, you know, and failures on some of that infrastructure there. I'm not so sure about onshore, so there would maybe be different contexts. That would
there'd be different root causes, I think. I mean, they've been quite specific about their root cause because it's been quite well known, cause a lot of outages, whereas in T&D, they've not got quite the same level of vulnerability to the elements, perhaps.
Yeah, but there is, of course, the aging infrastructure, you know, and the fact that is, you know, you want to maximise, you don't want to be taking things out of the ground that are still maybe get many years of service left in them. You know, there's been a lot of anecdotal sort of stuff in the past about, you know, cables were installed, but they were still there, you know, decades and decades beyond what maybe their original anticipated life would have been, which is probably a good thing. But of course, you would expect as they get older, the risk of an unexpected failure might increase. So perhaps putting this kind of monitoring to preempt things, maybe on a subset of the asset population, the aging population, or the most critical somehow, is certainly something that seems to be happening at the moment, and I'm sure that will increase.
Yeah, I can see that one question has come in, and I think it warrants going back a couple of slides and just going over something one more time, Neil, which is the principle of the CFD technique, because I think we glossed over that, but you know, we kind of made an assumption about the understanding, but I think we maybe need to just go over that. Maybe Stephen could just say a few words about how you use the currents to do a differential calculation, and that can be quite discriminative about whether the fault's on one side of a boundary or the other.
Yeah, sure. I mean, so what I'm really interested in, but from a protection point of view, is, you know, what happens in the first sort of few milliseconds of a fault occurring. And so this gives you, as Campbell was talking about earlier, it gives you, you know, sort of perfect discrimination through unit protection, through differential protection. So as long as the cable section is contained within that zone of unit protection, then we can, without any ambiguity, we can determine which section the fault occurred in. So in this particular example on the slide, obviously there's an undergrounded section sort of sandwiched in the middle between two overhead line sections. And so with a relatively simple amount of instrumentation, we can unambiguously detect what the fault is on the cable section. And therefore, back at the substation, which is potentially a great distance away, we can give a very reliable indication to the rest of the protection and control systems in the substation about whether or not to reclose, depending on whether the fault's on a cable or overhead line section. So it's, for me, it's a very simple, as I said, unambiguous indication, which the existing protection systems can readily make use of.
Yeah. So effectively a multi-zone differential where each section of the circuit, you know, so if you had 3 overhead and 3 underground sections, that would be 6 individual differential measured areas, and you would just look at the currents going in and out of each of those sections to identify when there's a difference. You know exactly in terms of the section where that fault would actually be.
And it's something that's classically very difficult to do with distance protection, where you've got, especially if you've got multiple cable sections dotted in between your overhead line sections, distance protection becomes much more difficult, because there's non-linearities involved there, and it's plausible, but it's very hard to, you know, give you 100% confirmation of where the fault is located.
Yeah. One question that's come through, which I think is worth hitting head on, which is, why would operators not use this type of system? Is it to do with the availability of fiber? And I mean, I guess Campbell could comment on policy of this for various operators. I guess at the end of the day, one of the decisions comes down to the balance between the risk of this fault happening and the outage, the cost of outage and dealing with that versus the cost of installing a system like this. And I think prior to maybe about 10 years ago, there wasn't really any optical techniques to deal with this sort of thing. So it was quite costly to instrument these remote sections. But once we now have sensors that can use the fiber, which often is there in a transmission system in particular, it becomes very cost effective to do this. And suddenly you've got a lot more information at your fingertips. So policies are probably likely to change.
Yeah, I would say so. I mean, clearly we are operating in quite a conservative industry for the right reasons. I mean, protection engineers should be probably the most conservative people in the company, but there is certainly, you know, because it's new, and that's a natural sometimes barrier to adoption. But I think, you know, the availability of fibre is not really an issue, certainly at transmission, because it's used, you know, for multiple purposes. As we all know, there's often several cores running, you know, either inside the conductors or wrapped around them along the same routes. So usually availability of fibre is not an issue.
I think as you go down to the distribution voltage levels, say 66 kV and under, that's when you start to encounter lack of fibre, and then it becomes a much more difficult decision for an operator to make because they would have to lay fibre, and that can be expensive, but a lot of operators already have fibre above that voltage level.
And I think that's something that may be changing, Philip. I mean, we know from our own research and our own contacts that, you know, and I noticed the question there, you know, there's a scope for pre-fault detection and distribution networks. Well, again, we would need the fibre there to enable our sensors, and I think the answer would be yes for that. But, you know, going back to the point about if fibre's available at distribution, it's perhaps not so available at the moment, but we are aware of some companies where it's been put in because clearly fibre's a massive piece of comms infrastructure, and with all of the, you know, the pervasiveness of communications, IoT and all that stuff, you know, there is an opportunity there for the distribution network to act as the communications backbone as well if fibre is placed alongside that.
Mm-hmm.
So I think that will change positively from our perspective in the future.
Yep. Do you want to just round off your slides, Neil, and then I'll just see what other questions have come up?
Yeah, so this is just really to recap what our kind of proposed solution is to this. This doesn't really cover a lot of the discussions that we're having, but I think we'll continue these as the questions come in.
Yeah.
So I'll maybe pass back to Saul, who might want to check on what
so one of the questions that came up here that I thought was an open one. So there was a question about whether sheath-induced voltage can be used for protection purposes as a reference.
Sheath current, yeah.
I can see those questions, so, and I can see the one that says, could the sheath-induced voltage be used for protection purposes as a reference? And then the last question that's coming in my screen, which is about, you know, it's quite a long question, you know, locating cable faults precisely, which minor section did their fault take place in? That, to be honest, that's something that we're not looking at in great detail, and it's not really the focus of today. And Philip, please feel free to come in, you know, but the exact identification of where the fault is down to the kind of meter resolution is not something that we are focused on at the moment. It's more the section, whether it's overhead or underground, and if it's underground, which section is it on, and therefore you would inhibit the auto reclose. I think that's the major driver behind what we're doing now. But if you have distributed measurements, of course, there are other things that you could do, and the precise fault location as opposed to faulted section identification is something that we're looking at, but I don't think we've got anything that we can say that we're doing right now.
I guess it depends on what the scope of this discussion is, because if this discussion is about cable fault detection, it's about that. And then, of course, there's a wider point to be made about what are the benefits of wider deployment of distributed sensing and what could be done with that. I wonder, Stephen, if there's anything you would like to say about that from in a wider sense of continuous point and wave monitoring, what could be seen?
Yeah, there's quite a good SIGRE report on this topic, SIGRE V5 report, which it looks at all the different technologies that can help here, and it highlights this. You know, it talks about this exact issue of using impedance as you know, to help you find the exact fault location, and it's quite hard. And part of the issue is also you need voltage measurements involved. which is potentially inconvenient or expensive as well. But yeah, there's potentially things we can look for when you've got high frequency monitoring of the signal, and that's something we're looking at exploring going forward.
I guess as soon as you introduce voltage, you have the complexity of getting an earth or getting a reference there, and then you've got the insulation challenges and the cost rack up for that, whereas current can be retrofitted very quickly.
Yeah.
One other angle here, Philip and Stephen, would be where you've got fiber either co-located or not co-located with the phase conductors, which would enable an OTDR fault location to be quite specific if it's contained with. Is that worth explaining?
Yeah, that's a very good point. If the optical fiber, as it is in a lot of subsea cable systems, is co-located with the conductor, as in it's in the same cable embedded, or it's very close, then a fault, which in a multi-phase cable will often be eventually catastrophic, will cause damage to the fiber at that point. Now there's a fiber technique that we build into our systems called OTDR, which is the optical equivalent of TDR. So it's reflectometry. It's looking for the time of flight of the light, which will reflect very strongly off a break. So once the faulted section has been identified, you can fire off your OTDR pulse and it'll detect your fault location to within a few centimeters. Now that's very high performance and a great technique for those situations where the fiber is embedded next to the conductor. In many distribution applications, if there's fiber that's in a duct nearby, which is not a problem for installation of electrical sensors, but it means that you can't use OTDR to do accurate fault location in that way. Hopefully that kind of answers that question. But it's certainly a very good technique for when you're offshore.
There's another question there that I can see that I could maybe answer. There's a and it's basically saying that when the overhead line is connected to cable, there's a change of impedance at that point, which will then, reflect signals from that discontinuity and impedance if this is traveling waves that we're talking about here. I think, and the question is how is this handled in terms of reducing the measurement sensitivity? So I would go back maybe to what we were saying earlier. For this faulted section identification, we're relying on measurements of the fundamental frequency components and looking at a simple differential comparison. So this wouldn't really impact at all on this kind of multi-zone differential. Of course, it would impact on traveling wave type electrical fault locations because there would be a lot of reflections there, but that is again not really the focus of what we're proposing to do with the system as it stands at the moment.
There's an interesting question here about the time synchronization, which we didn't touch about, but you can see that I guess the questioner is thinking about on a really long circuit, if you had, for example, multiple dips, you're receiving signals from one dip and you're receiving signals from another dip, and maybe you want to do some comparison between signals that are separated. Now, obviously, you have a finite speed of light in fiber, which is roughly the same as the speed of traveling wave in a conductor, by the way, which is a good rule of thumb. So you can see it takes whatever it is, takes a microsecond every 5 kilometers or something like that, Neil.
Roughly.
So I wonder if it's useful there's a slide at the end, I think, in your appendices where you talk about the time synchronization and how that's done, because it's quite interesting, I think, how that can be done with optics without needing any GPS access at the measurement locations.
Yep, let me just find it. It's in here somewhere. So essentially, yes, as I said when I was kind of introducing our solution, the interrogator itself takes a time synchronization source, but none of the sensors require this. And as Philip says, this is because we know very, very accurately what the speed of light is in the fiber. So that allows us to centrally timestamp all of our measurements for kind of direct comparison at that point. So, we can kind of ping each sensor location, which gives us a measurement of that time of flight, and then we just compensate for that effectively when we publish the measurements. And kind of uniquely amongst these sorts of schemes, we think this means that even if we lose time sync, all of our measurements will stay in relative sync, which is quite an important point when you're relying on GPS access to properly align your measurements. With our system, they would retain that relative sync, and so your CFD would remain functional, even in the event that you lose GPS access.
Yeah, which I guess saves you having to spread network time between two distant locations and make sure that you've got clocks synced at either end.
Yeah.
Yeah.
So a couple of other grouped questions, if I may, that I've been tracking across here. So Neil, could you go back to the point about batteries, energy scavenging and power supplies? Because I think people still had questions across the commentary here about how the technique actually gets a signal back from a remote location. Because I think it just bears another explanation, because there are too many questions asking about that again.
Of course, yeah, and it is an important kind of differentiator, is to say that we're not kind of like a wireless technology or an IoT type device, which would require, as you say, batteries and things like 4G access in order to communicate measurements, and those can be susceptible to, well, for one thing, the battery's failing, so you need regular maintenance, and there's various security concerns about using wireless transmission as well. So what we do with our sensors is we splice them, we hardwire them into the existing optical fiber in the network. So we would take a fiber from the OPGW, one end would go into our interrogator on the left-hand side of the screen here. And then at those transition points for CFD, we would just splice our sensors, kind of daisy chaining them into that network. So in series, we would have each of our sensors spliced into that fiber. Because it's hardwired in the fiber, you don't have to rely on wireless transmissions, and everything is just transmitted directly back to the interrogator. Another point to make is that all the sensors, there's no active electronics there. They're not necessarily transmitting a signal. The way it actually works is that our interrogator effectively pings each of the sensors, and we're looking at a reflected signal from each one. And the sensors do this passively, and in that reflection is encoded the measurement of the current at that point. That's an analog kind of signal in the light itself in the fiber. So there's no data outside the substation. There's no network packets involved. It's just an analog signal in the fiber. And as I say, we measure that by reflecting off each of the sensors at a very high rate and then measuring that back at the interrogation system. So because they work in reflection and because there's no active electronics, this is what gives you all these benefits of passive sensing, no local GPS required, no local telecoms equipment required at the sensor location.
So Neil, just for clarity, because we know where the sensors are, that's not just a network address that we know the physical location of it, and therefore we don't need GPS to understand where something is, say, underground.
Yes, that's kind of encoded in the reflection from each sensor, is its location and what it's measuring. We get all that in the reflection from each one.
Okay, and
Just
then,
conscious of time, so I don't want to take up anyone's time beyond the allotted slot.
that's a really good point. We've probably got a few more questions that we can answer offline at the back of this Q&A, of course.
Yeah. And of course, you'll be sharing the recording with everybody that attended.
Yes, so I should probably say at this point, and by the way, thank you to Philip, Neil, Stephen and Campbell for taking us through this stuff. As always with these sessions, we never get enough time to tell everyone everything and explain all of the applications and where it fits into the scheme of things. However, I've been trying to answer some questions live in the background, and clearly if we've got time, we'll continue this for the next 10 minutes to the end of the hour, but otherwise we'll be responding to you privately, and over the next few days we'll follow up with a copy of the recording of the session, and also we'll provide you with some written materials. I know a lot of you are asking for some more technical documentation, case studies and white papers, which we do have available. And for your information, most of that is actually on this website. Again, that's synapt.ec, Synaptec. You'll see application notes, case studies, white papers, technical information, and data sheets concerning the hardware and the system applications. Now, with that said, we should probably stop ourselves talking there. Thank all of you, in fact, so many of you, for turning up and asking so many useful questions. The ones we didn't get to live, we will come back to after this session. And then please keep in mind that on our events page on Synaptec, you'll also see the upcoming series of webinars that will take us through to the summer. There are more to follow, but very appreciative of the engagement and the amount of questions on this clearly relevant and important theme. So thank you for everybody. Appreciate your time today, and we'll be following up with all of you by email or in person as soon as we can.
Yeah. Thank you, everyone.